Got it. All right. Hi, everyone. Chris is our PI is on vacation this week, so I'm going to give just a brief status update. What's happening on the project side of Axis? The science teams are hard at work. We have 5 science working groups, and they're meeting on a weekly or bi-weekly basis. And right now, we just came off of a call for of all the leads of the science working groups, and everything seems to be going really well. And they're honing their top science cases right now. So what we've realized is that there's just so much more that Axis can do than can fit into a single science traceability matrix, which is a great thing because it really means that Axis is a true guest observer facility. So on the project side of things, the biggest thing that we have been working on is that there's this strategic science concept review that will take place in July, and that is basically, it's a 20-minute presentation to Goddard management. We need support from Goddard since they are building the mirrors and their lead partner, and we need, so Goddard needs to agree to support the Axis mission. And so we have been working really hard on a really nice presentation to present in July. Then in early September, we have what's called an instrument design lab run, where we basically work with engineers. We've decided that we're going to present to them kind of our fixed baseline, or like a fixed baseline mission. And they will help us understand like thermal controls, what do we need to know about pointing stability, and kind of working with the engineers to make sure that everything that we want to do with Axis we can do. And so that's a big hurdle that's one of the things that we're really ramping up towards. So in preparation for that ideal, since we want to make sure that we go in with a single point design, we are working hard now on kind of finalizing some of these mission parameters, and kind of working both with the instrument teams and also the science working groups to kind of make that ideal design. And then after that, we'll find a spacecraft vendor. So that's kind of where we're at with this process. The last thing is Adi Ford is she's one of the co-leads for the AGN science working group, but is also our communications lead, and has started up the Axis Probe Twitter account. So look out for awesome tweets. And if you have things that you want Axis, the Twitter to highlight, science that you want us to highlight, then please get in touch with her. Okay, so that's it from me, and I'll hand it back to Mike.
Okay, great. So our first speaker is going to be Stephen Walker, talking about revealing the X-ray faint connections to the cosmic web. So go ahead and...
Yeah. Hi, can you hear me?
Yes.
Good. Okay, I'm just going to share my screen now. Okay. So hopefully you can see what I'm seeing. Okay, good. Yeah, so I'm going to talk about basically looking at these filaments between galaxies, between clusters. So this simulation here, this is the Illustrious simulation, is basically showing our theoretical understanding of how large-scale structure formation happens in the universe. So this is a simulation of a large box of the universe starting at very high redshift. And what you're seeing on the left is the backbone of the cosmic web being formed, and it's due to the dark matter collapsing first. So all dark matter can do is collapse under its own gravity, so that collapses first. And then on the right, what you're seeing is the baryons. So the baryons are then collapsing into those gravitational potential wells at the nodes. That's where the galaxies and galaxy clusters are forming. Those the areas the gas is heated up to the highest temperatures, greater than 10⁷ Kelvin, and so they're the easiest bits to see. But in the local universe, around half of the baryons we expect to be in the intergalactic filaments of the cosmic web, which are basically the backbone for gas flows on cosmological scales. And we expect around half of the baryons to be in this warm, hot intergalactic medium at temperatures between 10 to the 7 and 10 to the 5 and 10 to the 7 Kelvin. Unfortunately, this gas is very diffuse, and so it's basically very, very difficult to observe. But due to AXIS's high sensitivity, hottest part of the warm, hot intergalactic medium, that between 1 million and 10 million Kelvin, can be revealed through its emission in the soft X-ray band. So this is from the Astro 2020 review on cosmic ecosystems, and that was emphasizing the need to basically understand this entire process of the way gas flows through galaxies. And so this beam basically is what I'm going to talk about, is basically this inflow of pristine gas onto galaxies. So that the actual wording is emphasizing the need in the Astro 2020 review to actually map the intergalactic medium in emission. So at present, these sort of studies are limited to absorption studies by looking at background quasars and bright sources and trying to see the WHIM in absorption, but we're talking about trying to actually see the emission coming from it. So this is another computer simulation. This is an X-ray. This is what you would see if you had a super amazing telescope. This is what you would see, all of the gas. Unfortunately, with things like Chandra and XMM Newton, we're basically limited to just the brightest nodes of this cosmic web. So at the moment, what we can see is that with Chandra. So a lot is missing. We are basically just seeing the tip of the iceberg of the baryons. So an analogy of this is that imagine trying to do a study of a city, how a city worked, how all of the population is moving through this city, but imagine that you could only see that. So this is sort of, we're trying to go from just looking at the brightest bits to actually doing a full census, understanding how these systems actually work in their entirety, how gas flows in and out of them. So this is a figure from the original AXIS report that was submitted to the decadal survey. And what that's showing is basically what the baseline specification for AXIS, how it would improve upon Chandra in terms of sensitivity. So Chandra could only really see and probe the sort of inner regions, the brightest X-ray regions. AXIS can probe out to this white contour, be able to probe in emission the intergalactic medium, the warm hot intergalactic medium in the vicinity of clusters. So what do we need in order for this to be possible? We obviously need a high effective area. We need more photons. We also need a large field of view. So this image is very big. You can see on the scale bar that that's a 5 megaparsec scale bar. So for context, this is how big in white the field of view of AXIS. If these filaments were at redshift 0.1, that's how big the field of view would be. If we were looking at redshift 0.2, then it would be the yellow box. But basically, we need a field of view that's going to be big enough that we can actually map these filaments in a reasonable observation time. We also need it to be big enough for us to be able to do simultaneous background measurements. So you want to be able to, in one observation, observe your source and the background at the same time. And this is important because when you get down to these low X-ray surface brightnesses, I think this just low surface brightnesses, some of the important background components are very time variable. And one in particular, which is a cosmic nuisance, is this solar wind charge exchange. So that comes about in our solar system. It's very time variable because basically the sun, solar wind is time variable, and that can lead to all sorts of horrible emission lines in the soft X-ray band, which vary with time. And so you basically want to be able to model these and take them out. And so you need to measure these at the same time. You can't just do your background observation 6 months later. These lines would be completely different if you did that. Another important thing is to be able to reject stray light. So stray light is when say you have a bright object and you're trying to look at your faint object next to a bright object. So for instance, if you're trying to do this observation here, you could get light scattered in due to the sort of bright X-ray galaxy cluster core. So we need to be able to reject stray light. So this is showing stray light with Suzaku. So this is the offsets for the Crab nebula. So right in the middle is the Crab nebula. And then all of this emission is just light that has been scattered into the telescope, has gotten past the pre-collimator. So you're thinking, okay, well, that's the Crab, so surely clusters aren't that bright. But this is an example from Erizida. So this is the Coma cluster, the outskirts of the Coma cluster studied with Erizida. And what you're seeing is that as you try to measure the X-ray surface brightness profile out to very large radius, so we're talking about, in order to probe these filaments, we need to be able to get out to sort of this level of X-ray surface brightness. Even with Erizida, the stray light was starting to become a sort of dominant, important component to the background that needs to be either thoroughly understood and removed or not there in the first place. So the good news with Axis is that, so this is information from Will, this is what Will Zhang told me, is that basically the way the mirror is built will allow for some very elaborate stray light baffles, which will basically block out stray light from bright nearby objects. And this should be better than any other X-ray telescope. So I think this is a really big selling point in terms of studying low X-ray surface brightness emission. And in fact, basically what Will Zhang told me is that under most circumstances, we'll get a pretty clean field of view, and that within 20 arc minutes, you're basically free of stray light, which would be amazing. For me, that's a very, very important thing. So obviously low surface brightness, you'll need a low background, but you also need a stable background. So low isn't enough. If you're low, but you're varying up and down, if your background's varying up and down in an unpredictable way, that's not very good. You need it to be stable, predictable. You need to be able to reproduce the background with a very high, the particle background with a very high level of accuracy and take it off. So that I'm stressing that it's not just the level of the background that's important, but actually our understanding of how stable it is, how accurately we can reproduce it. So with Suzaku, so obviously being in a low Earth orbit is a big help, and Suzaku and Rosa are the two missions that have had this low Earth orbit and low particle background. With Suzaku in particular, what was really good is that it had a large database of night Earth observations that were being taken throughout the mission. That basically allowed the particle background to be reproduced with an accuracy of about 3 to 4%, which was really what enabled the high, basically allowing us to model spectra out into the outskirts of clusters and to very faint X-ray surface brightness regions. So it's the ability to reproduce the particle background. So the next few figures I'm going to show are from this white paper that I wrote or led for the decadal survey. This is going to emphasize the need for the PSF. So what you could see in that coma image is that the Erizida coma image is that there's an awful lot of point sources out there. So we're wanting to probe out into these regions, but there's a lot of point sources due to background AGN, which we need to get rid of. So we need good arc second level PSF in order to find them all. This is the figures from the white paper I'm talking about. This is a simulation of a galaxy cluster with what you can see with Chandra. So you can just see the brightest regions, and then this is showing all of the horrible sort of point sources. For this science, they're horrible because we just want to get rid of them. And this is what I'm going to show is what Axis would be able to do, observing exactly the same thing. So you're basically getting the full story. You're being able to see the filaments connecting to it. All of the infall galaxies, you're being able to see. Basically, you've gone from seeing the tip of the iceberg. Look at this guy. You're just seeing the head. You would never guess that it was moving to the right, but suddenly all of the details of the gas or the bottom part of the iceberg is being revealed. Another important thing with the PSF is that the simulations tell us that there's a whole load of multi-phase gas clumps in these regions. And currently with Chandra, you either can't see them because they're not bright enough. So for instance, I think this one, I don't know if you can see my mouse cursor, but this one disappears. And the brightest ones with Chandra, you can't tell them apart from point sources, so from background AGN. So there's a huge confusion there. Okay, so yeah, and the other thing I'll emphasize is that need for very good PSF over a large field of view. It's not good enough to have good PSF just on Axis. It needs to be across the whole field of view, which Axis is able to do. So yeah, so the simulations that we have of basically galaxy and galaxy cluster formation predict a huge amount of complex activity. This is a simulation from Oppenheimer of forming galaxy clusters as a density, and you just see the huge amount of structure that these simulations are predicting. And at present, this is completely untested observationally. We simply can't see it. It's all below the water level of the iceberg. So there's a huge range of discovery space that would be opened up with this. We would actually be able to test our theoretical understanding of how these structures form, how gases flow in through these intergalactic medium filaments. This is the temperature map showing complex temperature structure. This is the metal abundance map showing the complex distribution of metals, which you would need to understand in order to sort of test these simulations. So these are the big questions. We're wanting to know how do these structures grow? How are the metals distributed in the cosmic web? And what I'm about to finish, but basically this allows us in a way to view the interplay between feedback from AGN and gravitational collapse, and how that tug of war has played out throughout cosmic time. Because Axis will allow us to produce this basically an almost complete survey of the baryons. So what am I talking about? This is a illustrious simulation of metal distribution in filaments, in the WHIM filaments. So I'm just going to end by illustrating this about AGN feedback. So this is a simulation of a galaxy cluster forming from high redshift 2 all the way to a lower redshift. And what you're seeing are basically the metals produced by individual galaxies. So each speck is basically a galaxy, and the color is basically the metals that have been produced by the stars in that galaxy. And over time, all the galaxies are kind of falling together to form the cluster. And in this simulation, there's very little AGN feedback. And so in the galaxies, the metals aren't spread out very much. Basically, the metals in this simulation stay roughly nearby each galaxy. And then as the cluster forms, you get this sort of distribution. However, if we turn on the AGN feedback, you'll see that the AGN feedback is able to spread out the metals from the galaxies much more. So that's turning on the AGN feedback. So you can see in the metal distribution the effect of the AGN feedback in all of these galaxies, dramatically changing the distribution of metals. And that actually changes when you finally get your galaxy cluster in the local universe, the low redshift, when you measure the metal abundance profile, basically how the metal abundance in the galaxy cluster is varying from the center to the outskirts. If AGN in the galaxies that formed the galaxy cluster have spread out the metals a lot, then you're expecting basically this is a metal abundance and this is distance from the center of the galaxy cluster. You'd expect something like the black line, where in the outskirts the metal abundance is flat, and that's because the AGN have spread out all of the metals, and you expect a uniform distribution. If that hasn't happened, if instead the metals are kind of all just stuck next to the galaxies, you would instead expect an abundance profile, that the metal abundance profile that follows more like this dashed red line. This is showing how the interplay between feedback and gravitational collapse, how we can study that. So the aim would be to, one of the aims would be to measure metal abundances out to very, very large radii, of up to 2 times R200. This just goes up to 1 times R200. Okay, so this is a summary. So the decadal survey emphasized the need to map intergalactic medium and emission axis with its high sensitivity. Will be able to make great inroads into this and reveal some of these hidden drivers in the way that galaxies and clusters of galaxies form. Thank you. So that's it. I guess I stopped sharing maybe. There you go.
Okay, great. So yeah, we can take some questions now. I will ask one just while we're kind of getting ready. So there's a new instrument on KEK, which is the Cosmic Web Imager. That's sort of this large field IFU in the sort of blue region. And I've seen some of their press releases that they've used gravitational lenses to looked at distant damp Lyman alpha systems. And I'm just wondering how the X-rays kind of work together, or maybe not, with some of the blue measurements of the cosmic web, and whether we can use gravitational lensing to help look at some of these structures, or just curious about that.
Yeah, I mean, basically we're talking about measuring the WHIM at low redshift right now. So the missing baryons is right now. If you go back to high redshift, we can see them with the Lyman alpha forest. Mm-hmm. So it's because as the universe has aged, the gas has become more tenuous, and you can't see it with Lyman alpha, the Lyman alpha forest anymore. Yeah, but obviously this is a multi-wave. This axis would be part of a multi-wavelength attack on trying to find all of the intergalactic medium at lower temperatures. We're looking at UV absorption lines. So it will be, in order to fully reveal everything, we would need a axis would be combined with other instruments and other wave bands. But this right now is a big gaping gap in our capability that we can't do this. Yeah.
Okay, great. Yeah, that makes a lot of sense. At low redshift, you have the best sensitivity. Yeah. So you can do quite a bit better. So in the chat, I see Nico asked, what energy resolution do you need to detect the WHIM?
So the current baseline of access should allow us to basically, I mean, a lot of this emission is coming out of the oxygen 7 and oxygen 8 lines. Obviously, we don't have a calorimeter, we don't have a grading. So in an ideal world, you would have all of those things, but the current baseline is enough to be able to measure the excess emission from the WHIM. And if you carefully model all of your background components, we've been simulating that basically with 100 kilosecond depth, you can get out to the sensitivity required to do this.
Okay, so I saw Richard Rothschild had a question. Oh, okay, he asked it here. The simulations show the image filled with diffuse flux. Where do you get the background if you have all this diffuse flux?
Yeah, so the I'm not sure what was I just share again, but I think what's being referred to, yeah, basically you're going to need your field of view to sort of reach out into a void. Exactly how we do this is sort of what we're working on right now. Ideally you would have a huge field of view. So the 24 by 24 arcminute baseline at redshift 0.1 we found is enough to, in most cases, allow us to have a relatively X-ray free emission region to do the background in. So this is probably a bit misleading because it's really overemphasizing how bright some bits of the WHIM are. Basically outside of that white contour that Axis can see, this blue stuff is super faint. So it's you really do have to play with the color bar on this to actually get it to be visible. When you do this on DS9, it's huge dynamic range that you're looking at.
Okay, so maybe I'll ask one more question. If anybody else has a question, please raise your hand. But so what do you see the survey strategy for these types of sources? I mean, I can imagine going deep on some or.
Yeah. So we can use, just showing this again. So we can use the actual galaxy distributions. We sort of know where the filament should be based on galaxy, redshift surveys. So we can basically follow along where we see the actual filaments of galaxies. So I can imagine if we did this at redshift 0.1, so that the field of view would be the white square, we would be sort of covering along these directions. And yeah, basically I worked out that you can pretty much cover all of this in about a megasecond. So each observation needs to have a depth of 100 kiloseconds. That allows you to resolve out the point sources and actually accumulate enough photons. Obviously, we don't have to do the bright regions because they can be done with other telescopes, so we can miss those bits out. And but yeah, that's sort of the strategy that we would be aiming for clusters, I think, around redshift 0 or filaments around redshift 0.1. If you go closer than that, then the field of view is too small to fit everything in. And then if you go too high a redshift, then the emission gets fainter because it's further away. Yeah, that's what I'm working on right now, doing lots and lots of megasecond simulations of how to best do this. So if anyone wants to volunteer to help, I'm more than happy to have any volunteers.
Great. Yeah. So contact Stephen if you have any ideas. Great. So let's switch to the next speaker, who will be Kelvin Burdge, telling us about discovering and characterizing LISA gravitational wave sources. Go ahead.
All right. So let me get the talk up. Can you see this?
Yes.
Okay, awesome. Yeah, so I'm really excited to be giving a talk today on sort of my thoughts on how we can use AXIS to discover and characterize millihertz sources of gravitational radiation. And I want to emphasize one thing in this title. I include the word discover, and it's because we don't actually need the gravitational waves from these sources to find them. And so just some quick background, because I'm not going to assume everyone here is super familiar with gravitational waves, is basically gravitational waves are self-propagating perturbations in the space-time metric that originate from the time evolution of a quadrupole moment of a mass distribution. And it just so happens that the types of gravitational waves that we can detect in our own solar system with the detectors we're developing largely arise from when you have two very dense objects like stellar remnants orbiting each other in a very close binary system. And one example of such objects are objects that have been detected by LIGO. You can see one of the detectors featured there on the right, and those are primarily double black hole and double neutron star systems. And so the big pitch of why gravitational waves are revolutionizing astronomy is basically it's given us a completely new way to probe and study the most extreme forms of matter in the universe. And so I'm going to shift gears a little bit in this talk to talk about not LIGO, but an upcoming space-based gravitational wave detector, LISA. And so LISA is going to change this game significantly in the mid-2030s because it's going to give us access to lower frequency gravitational waves than what LIGO can see. And when you go to low frequencies, you actually get astrophysically distinct classes of sources that LIGO is not sensitive to. And in particular, the sources I'm going to be talking about in this talk that I'm thinking about looking for with access are sources in our own galaxy. So one of the amazing things with LISA is when the detector turns on, within like a year or two of collecting data, we're going to have a list of tens of thousands of persistent sources of gravitational radiation in our own backyard, in the Milky Way. And the amazing thing about these sources is, one, they're persistent. So unlike the LIGO sources, which merge and are gone, these are going to stick around for thousands of years or tens of thousands or even hundreds of thousands of years before merging. And that means that we can use them to drive development of new instrumentation. We may find one and decide, hey, we need some new state-of-the-art UV facility to answer this question about it. And it's not going to go anywhere. It's going to stay there long enough for us to build any facility we want to. But the other amazing thing about these sources is they're tens of thousands of sources, and they're almost all multi-messenger sources. And that's because almost all of these sources in our own galaxy come from this particular class of sources. So I'm showing here sort of the broad landscape of sources that one can detect with gravitational radiation. And the ones we're very familiar with are the ones on the right that LIGO is detecting. At this intermediate frequency range, the vast majority of these sources are these resolvable and unresolvable galactic binaries. And those sources almost all contain at least one white dwarf, so electron degenerate matter. And the great thing about that form of matter is it actually emits light in the optical. When it interacts with the compact object companion, whether that companion is a black hole, a neutron star, or a white dwarf, doesn't matter. You're going to get X-rays when you're accreting in such an extreme system. And so just a quick sense of scale, white dwarfs are roughly about the size of the Earth and weigh as much as the sun. So not quite as dense as a black hole or a neutron star, but still something completely outlandish compared to anything we're used to here on Earth. And one of the wonderful properties of electron degenerate matter is we actually understand its equation of state reasonably well, and we can approximate it as a degenerate Fermi gas. And so this is actually kind of important in thinking about why access is such a powerful tool for these systems. So in the top plot here, you can take that equation of state and basically write down a mass radius relation. Just what is the radius of gravitationally bound electron degenerate matter as a function of the mass of that gravitationally bound body. And that relation also lets you write down a density relation, which I show in the lower plot. And recasting this in terms of density is particularly useful when thinking about degenerate objects and binary systems, because there's this remarkable relation. And I will say, if you take nothing else away from this talk, I hope you remember this relation, because it's a remarkable property which anyone who works on binary systems should abuse all the time. And the property is basically that the orbital period at which an object will overflow its Roche lobe in units of days is approximately equal to 0.43 divided by the square root of its density in grams per centimeter cubed. You don't need to do any kind of sophisticated modeling of what the compact object is, because this is so insensitive to the mass ratio. It works to within a few percent for mass ratios up to 100. And that's why it's a relation that we like to use again and again, because it just simplifies thinking about these systems so much. And in particular, why this relation is so useful in the context of access is the following. Say I have a gravitational wave source that LISA detects. I know the orbital frequency from LISA. And say I point access at its error circle. So usually the localizations here are going to be on the order of square degrees. A few axis pointings can tile the entire error circle. Well, the idea is say I find an X-ray counterpart that is periodically modulating its X-ray flux at the gravitational wave frequency, which I already know, so it's pretty easy to pick out. Well, then I know the orbital period. Well, if I know the orbital period and I know that they're X-ray photons, well, the X-ray photons tell me that there's Roche-Lobe overflow. You don't get X-ray photons from these systems unless there is Roche-Lobe overflow typically. Well, if I know the orbital period and I know it's overflowing its Roche-Lobe, I know the density of the donor. Well, if I know the density of the donor, I can use this bottom plot to tell you what the mass of the donor is. If I know the mass of the donor, and I know something like the gravitational wave strain, or for example, the chirp mass from the frequency evolution, I know the mass of the accretor. I basically solved for both masses of the system simply on the basis of seeing some X-ray photons without any further detailed analysis, thanks to this wonderful relation. So just a pitch of why the synergy is particularly powerful. And I'm going to talk about more specifics of why AXIS is the X-ray facility to do it in a moment. But the other thing I just want to mention is you can take this relation and basically convert the bottom plot into a characteristic orbital period at which electron degenerate matter will interact with the companion. And you can see on the y-axis there that that's typically between 10 to the 1 and 10 to the 3 seconds. Well, if you want to get the gravitational wave frequency, you can take 2 divided by that and go right back to our LISA plot and see exactly why LISA is such a natural tool for identifying electron degenerate matter interacting with another compact object. So now what I'm going to tell you about is why we don't even need LISA to find these. And I'm going to talk about a lot of my work here, which has been done in the optical, but then at the end of the talk, I want to convince you that we can actually do this in the X-rays as well, and AXIS is the perfect tool to do it. So what you're seeing here are optical light curves of 15 sources of gravitational radiation that I identified using photometry from the Zwicky Transient Facility, which is an all-sky optical survey in the Northern Hemisphere. And the basic idea is the way you find these is if you have a survey that is repeatedly sampling the fluxes of objects, be that optical flux or X-ray flux or infrared flux, many of these gravitational wave sources modulate their flux at their orbital frequency or some multiple of it. And there are 2 main physical effects that lead to this, at least in the optical, and those are eclipses, as you can see those in the movie on the left, or what we call ellipsoidal variation, which you see in the movie on the right, where basically the donor object is being deformed by the denser object. And there's a geometric effect that gives you a modulation at twice the orbital frequency. In the X-rays, of course, a lot of this modulation is going to come from an accretion spot that's potentially going to be occulted by the donor. Or just occulted by part of the disk or so on. And I'll talk more about that in a moment. But the big thing I want to also emphasize here is a lot of people sort of treat these as tools for calibrating LISA, but I want to just emphasize how information rich the electromagnetic signals of these objects are and how much we can learn by studying them only in the electromagnetic. And the example I'm showing here is a binary I discovered with a 7-minute orbital period. It's a double eclipsing white dwarf. You can see a movie of it on the left disappearing periodically as it goes into total eclipse. Pretty amazing this happens every 7 minutes. I'm just going to show this as a quick example of what you can do with an optical light curve, and then we can talk about what one can do with an X-ray light curve. But basically, just looking at the optical light curve, you can immediately see that there's the strong modulation out of eclipse. That's coming from the fact that one object is heavily irradiating the other. There's a shallow secondary eclipse at the peak of that irradiation, but the important feature here is there's a deep primary eclipse. And let's just look at the light curve and talk about all the things we can immediately read off of it just with a cursory glance. Well, one, we know the inclination is close to edge on. There's an eclipse. And if you model it, you can get it to better than 1/10 of a degree. Another thing you immediately know is object 1, where object 1 is the one being occulted during that very deep eclipse, is much, much hotter than object 2. And that's why that eclipse is so deep. It's producing the lion's share of the optical luminosity in the system. And then you can also actually, just by looking at that eclipse, immediately infer that, well, object 1 has to be smaller than object 2 because object 2 is big enough to completely occult it, hence the total eclipse that goes down to zero flux. And then using that white dwarf equation of state I mentioned earlier, you can also immediately infer that, well, this hotter, smaller object is the more massive of the two, because we know more massive white dwarfs are smaller in radii. And you can imagine when I model this, I can do much better than write down inequalities. I get very precise estimates. But I just want to emphasize this sort of, the gravitational waves are going to be an icing on the cake, but most of the science to be done with these objects is really in their electromagnetic flux. And I want to emphasize that that electromagnetic flux is extremely interesting at other bands as well. So I just showed you all this stuff in the optical. Here's what it looks like in the ultraviolet with HST. Very different looking light curve in a lot of ways, right? That irradiation is completely gone. And that tells us about some of the physics in the system, namely that the radiation is not being reprocessed in the UV. And similarly, as I'm going to show in a moment, for some X-rays, the X-ray flux is very informative as well. And so one thing I want to say of why it's so useful to be finding these things now, well ahead of when LISA flies, is one thing it lets you do is time the systems and actually monitor their orbital decay due to gravitational wave emission. And here's a plot of just 4 systems I did that for in the optical. The reason you can do it is you can time the modulation very, very precisely. And I want to emphasize that I have done this a lot in the optical, but it's also been done in the X-rays. And there's a particularly remarkable example of the shortest period binary we know of in the Milky Way right now is called HM Cancri. It's got a 5.35 minute orbital period, and it's basically a white dwarf accreting onto another white dwarf in a form of accretion called direct impact accretion. And this is just a snapshot out of a recent paper by Todd Strohmeyer, which has this sort of beautiful result of timing this system for decades now using X-ray facilities like Chandra and NICER. What he was able to do is not only measure the orbital decay of this system, so it is still on the way in. We've known that for a while, but just recently demonstrated that there's actually an F double dot that's detectable, and that the orbital decay rate is slowly slowing, and that the system we actually expect may turn around in the not so distant future. This was all enabled by the fact that if you look in the lower right-hand corner, it is figure 7 there, that the X-ray flux in the system is basically 100% modulated on the orbital period. And the general picture is there's an accretion spot on the accreting white dwarf that gets eclipsed during the orbit. And you basically lose your X-ray photons during that eclipse. And so I should say, the way the system was discovered was actually because of that modulation. People found it in ROSAT and saw there's this periodic source with a 5-minute period. People originally thought it was an intermediate polar, but now we know through further observations also in the optical that there are actually Doppler shifts and everything happening on this period, and that it's a double white dwarf binary. And so the thing I want to emphasize is if you look at this plot, the LISA sensitivity curve is the solid black line. So basically anything above it, LISA should be able to blindly detect. And as of 2018, all the known sources are represented by those black diamonds you see. In a couple of years, I added all of those red points to the plot using the Zwicky transient facility, basically this optical search. But I want to emphasize, if you look at the known sources, the 2 shortest period ones were both discovered because they were ROSAT sources. They're X-ray sources, and they're among the loudest LISA sources known. They're way above the sensitivity curve. Most of the rest of the previously known sources were just discovered because they were optically outbursting. And there are lots of people looking for transients and not doing this kind of Fourier analysis that was the key to unlocking all these other sources. So just as a proof of concept, we know we can find these using X-ray missions because the strongest gravitational wave source we know, HM Cancri, is found exactly that way. And so let me talk a little bit about why AXIS is the perfect tool for furthering this science. Well, one is it's well matched to LISA localization regions. So once LISA flies, if AXIS is still operating, it can basically just go in and find the error circles that LISA reports on the order of a few square degrees potentially, and just tile the error circle and get deep X-ray observations of the entire region. And then the idea is as simple as taking a Fourier transform of every single source in that region, and looking for the one that has the right component in its frequency spectrum, like HM Cancri you see there on the right. And the idea is that's really easy to do because you already know the frequency from LISA. That's how it's detected by the gravitational wave detector. So it's not a blind search, it's actually a highly targeted search. But the good news is because these things have such strong modulation, we don't actually need LISA to do that. We can already start surveying the sky and just look for sources that are strongly modulating their X-ray flux, and then further follow them up to identify these sources. And one thing we've been talking about with AXIS is the potential of doing a survey of the galactic plane, which is where most of these sources live, to do exactly this exercise and basically repeat the exercise that I've done with CTF, but in the X-rays. And that's going to be a very important thing to do because a lot of these sources are very bright X-ray sources, especially the interacting ones that may be behind a lot of dust where their UV flux doesn't necessarily get through the galactic plane's extinction nearly as well as the X-ray flux, though that is also attenuated to some degree. The other thing I want to mention is that the PSF is really important with AXIS. And this is important because if you look at something like a globular cluster, you can see an image of 47 Tug taken with Chandra there on the right. The source density is quite high. And you don't necessarily know ahead of time which source is the gravitational wave source. So the idea is that you want that tight PSF over the full field of view so that you can search them all. And this is also important in the plane, not just because of confusion of crowding of point sources, but because the diffuse background is quite high. And so having that tight PSF gives you significant sensitivity advantages over something like E Rosita. And then the key is also the boost in effective area of AXIS over something like Chandra also allows it to give you enough photons to actually do significant timing work. And you might ask, well, why don't we just use something like NICER? Well, the problem with NICER is when you look in these dense regions where these sources are, you get drowned out by the shot noise of all the other X-ray sources in your PSF. So it's necessary both to have the counts, but to also have the high angular resolution to do this kind of work. And so I just want to talk about a couple new results of accreting sources that I found in the optical, which have been pretty high profile results as kind of a motivation of why we really need an X-ray mission to look for more of these. This particular one has a 51-minute period that I just submitted a paper on. You can see it's eclipsing, so you immediately know, okay, this must involve two white dwarfs. And that was my thought immediately. There's strong tidal deformation that you see in that sinusoidal modulation out of eclipse. So I thought, okay, this is a pretty low mass white dwarf overflowing its Roche-Low bond to a CO white dwarf. And most astronomers would go, oh, that's kind of boring. Like, why do you need to find more of these if you already know a bunch? What's amazing about the system is, one, it's a double eclipser. So you can see a primary and secondary eclipse. Using that and the fact that it's overflowing its Roche-Low, those two properties alone let me solve the masses, the inclination, the radii, and the temperatures of both of these objects to exquisite precision. So better than sort of a few percent, which is actually pretty rare in systems involving white dwarfs. But the amazing thing about this system is I took a spectrum. That does not look like a white dwarf. That looks like an F-type main sequence star. And if you know anything about main sequence stars and binaries, you'll go, wait a minute, F-type main sequence stars cannot fit into 51-minute orbits. And you can know that from that relation I showed earlier, that the density of an object determines its period of Roche-Low overflow. An F-type star is going to be overflowing its Roche-Low at a 10-hour period, not a 51-minute period. What this actually is something called an evolved CV. So it's a cataclysmic variable where basically mass transfer occurred near the end of the red giant branch. And basically that object has been whittled away now to only its core. So there's a helium core with a little bit of hydrogen on it. This is a binary evolution channel, which people have proposed has been an essential progenitor channel for a lot of the ultra compact sources LISA will see. This is the first really clean example demonstrating that, yes, this channel is not only viable for producing those sources, but this one is already evolved well into ultra compact territory. And we can actually make really detailed MESA models thanks to the parameter constraints we get from these systems. But before I finish with this system, the thing I want to mention is there is an accretion disk in this system. You can't see it so easily in that spectrum because I've co-added this in the rest frame of the donor, but there is a double peak Balmer emission, double peak helium emission, calcium emission. So this is exactly the type of source we would expect to be able to pick up in the X-rays as well. Okay, I'm going to move on to one more source before I wrap up and just say there's another source I'm working on right now. This one has a much shorter period, 13.7 minutes, which puts it comfortably in the LISA band. It's mass transferring. It's a very unique mass transferring source because we see it's eclipsing. So there's an accreting white dwarf accreting from a low mass donor that's being fully eclipsed. But the remarkable thing is, unlike every other ultra compact mass transferring source known, where you basically can't see the donors, they're always very low temperatures. This one, we actually have a hot donor that's 20 to 30,000 Kelvin. And so the remarkable thing is that secondary eclipse, which you see is very broad and kind of triangular, is actually the accretion disk transiting the donor. So we can actually probe the structure of the accretion disk in this system in a way that is impossible with the systems where you can't see the donor. And the reason I showed the system as an example in an Access talk, you'll see in a moment, but one, it's mass transferring, which should give you a hint that there's going to be some X-ray flux. But the remarkable thing about these classes of sources where you can see the donor is you can actually measure their RV semi-amplitude. You can see the RV semi-amplitude in the system is close to 800 kilometers per second, which, by the way, is the largest RV semi-amplitude, to my knowledge, ever measured in a binary system. We're getting to the point where Doppler beaming and things like that certainly manifest themselves. LISA detectable, as I mentioned. But the important thing is we looked at it with Chandra. There are X-ray photons. There are not quite enough photons with Chandra. We only had 24 from this source to say that we picked up the periodicity. But if you had 10 times the effective area, I would clearly expect to be able to see the eclipse in this system. And so this is exactly the type of system which I expect we could use Access to find many more of, which is not always so trivial in the optical because of contributions from the accretion disk and so on. So there is still a lot of selection bias in this work that's only using optical data. And I should say the other really cool thing is I timed it using archival data sets like the Palomar Transient Factory, Atlas, and then follow-up observations I did with a high-speed photometer called Chimera to basically measure the orbital decay using historical data. Similarly, I'm expecting with Access, we're going to find a bunch of these in the galactic plane just using Access before LISA. But then when LISA turns on, we'll find lots more in the archival Access data and immediately be able to pull out their F dots because we've got such a long baseline of measurements built up from that historical survey. And that's a huge value addition to what LISA gives you, because in the end, the gravitational waves don't contain that much information. And LISA lacks the frequency resolution to get the orbital evolution for a lot of the, especially lower frequency systems. And another one I'll just briefly mention is I have another sub 8-minute period binary I'm working on, also mass transferring. You can see the booming helium emission in the spectrum below. This is a more typical source where you don't see the donor, but you can see Doppler shifts of the accretor in this case. Another type of system that we expect to be in the class of systems that Access will be able to detect, because these are extremely high mass transfer rate systems. And also, of course, comfortably in the LISA band. This one will be very high signal to noise. You could see something like this at 30, 40 kiloparsecs with LISA. And so a couple takeaway messages as I wrap up is, well, one is, I just told you, there are greater than 10 to the 4 multi-messenger sources coming in the next decade. And we don't need to wait a decade to start finding them. I think this should get everyone in the entire astronomical community excited. I expect arXiv is going to be full of papers of these sources as we find more and more of them. And frankly, I'm pretty confident Access is poised to be the premier X-ray facility for studying these gravitational wave sources in the next few years when it launches. There's not going to be anything really competitive with it for this type of work for some of the reasons I outlined. And then the last point I just want to mention is, I know in my experience in astronomy that a lot of our communities tend to be pretty insulated from each other. There's kind of the bubble of the X-ray astronomy community, the optical community, the gravitational wave community. But I think this kind of science case really illustrates why it's so important that we start training more broadband astronomers who are able to work at different wavelengths. And that's one of the reasons I so eagerly joined the AXIS effort. All of my background so far has mainly been in optical astronomy, but now I'm learning to work with X-ray photons. I'm eager to work with gravitational waves, and I'm hoping that we get more and more of that kind of thinking. And I think that's one of the reasons the decadal has pushed the multi-messenger idea so much. Okay, I'm out of time, so I'm going to wrap up there. Thank you.
Great talk. That was really interesting. So while people are thinking about questions, please just raise your hand or post a question in the chat. So you mentioned a few of them that were detected by Rosat. So I'm curious, you talked a lot about, following up LISA sources and some of the new ones we can detect. So if you're doing like a galactic plane survey or some of these other ones, would you expect to find them? Would you have to go back and look at the same area, or how does that work?
Yeah, so I think the idea is you need to acquire enough samples to be able to pick up the signal in the power spectrum. So it's all about the sampling. But the key is when we talk about sampling here, this isn't like looking for a pulsar where you're looking for millisecond periods. The periods are on the order of minutes. So what you really want is either one continuous, maybe 2 kilosecond exposure, where you basically cover an entire period and you see the X-rays come and go. Or you take a more cadence strategy like ZTF and actually come back and do shorter exposures, say 100-second or even 50-second exposures, and accumulate, say, 100 of those over the course of a year or two. The nice thing about doing the longer baseline is it also lets you pick up on the orbital decay rate, which you would never see if you just looked at 1 or 2 cycles with a continuous exposure.
Okay. Great. So I see a question from Martin. You can go ahead.
Oh, yes. Nice talk. I may have missed this, but one of the things that occurred to me as you're giving your talk is, are you going to be able to identify white dwarfs that are close to the Chandrasekhar mass or doubly degenerate systems that are about to merge? I.e., can you find progenitors of type 1a supernovae?
That we definitely can. And I actually think this is one of the most compelling science cases for the LISA era. I have my fingers crossed that LISA turns on. When LISA turns on, we will immediately know where all the shortest period white dwarfs are in the Milky Way, and even a few maybe in Andromeda, and certainly in the LMC and SMC. If we're lucky, I mean, type 1As are not that rare. The rate is sort of maybe order once per century or something for supernovas. LISA may turn on and say, hey, look here, there's going to be a merger in the next 10 years and a type 1A should go off. There are pretty good chances that that source is going to be somewhere near the galactic center, many kiloparsecs away behind a lot of dust. And the best tools we have are looking at wavelengths where we can actually still see the fluxes from the system. For example, the X-rays. Also the infrared. I think optical is going to be challenging there. But yeah, I think the answer is if we're lucky and we actually have a type 1A progenitor that's going to go off in the next couple decades, we'll have our answer about the progenitor. We'll definitively know whether the double degenerate channel is a type 1A channel or not. LISA will answer that question.
So you'll see them if they are there.
Exactly. Not only will we see them, we will be able to measure masses and all sorts of properties to exquisite precision.
Great. That's what I wanted to hear.
Yeah, if we get the photons. So the key is this gravitational waves alone don't do the trick. It'll tell you there's a high Chirp mass thing merging, but it's not going to tell you details about the component masses. You need X-ray photons, infrared photons, and so on.
Okay, that's really cool. Thank you.
Great. So we are actually at the top of the hour. So if anybody else has questions, please just contact Kevin. And so we'll have another talk in a month on Friday, August 5th, focused on AGN. But thanks everyone for coming. Great to see everyone and hear these talks. And everyone have a great holiday weekend if you're in the US and Canada. So great to see everybody.